Good afternoon, everyone. Today I'm going to be presenting the paper from IGCV 2022, Learning to Prompt for Vision Language Models. Let's get started. Training categories in visual recognition system, like modern CNN system, are often represented as a textual labels, and then they are converted to discrete labels for ease of computation. And changing those labels to discrete labels, they limit the systems to the closed set visual concepts and make it unable to deal with new categories without additional data or learning a new classifiers. So in other words, like when we just use labels as a labels and don't let the model learn more from those, when we add new classes or new data to the model, it requires more training. So this is where this paper comes. Large pre-trained vision language models like CLIP mainly, they shown a great potential and they learn representation that are transferable across wide range of downstream tasks. So vision language pre-trained align image and text in common feature space, and they allow zero-shot transfer to downstream tasks via prompting. Like this means that the classification layers are synthesized for natural language describing classes of interest. So I will talk more about this prompting and later on. So in this work, we exploit the potential of pre-trained vision language models for downstream tasks and identify a major challenge for deploying such model in practice. So yeah, here a little bit visualization about prompt engineering. So yeah, as we talked before, the CLIP uses the text and then image features to get higher accuracy. As you can see in the first, like just by adding a class, which gives much higher accuracy, then we can add some other additional words, which increase the accuracy by up to 4%, as you can see in the first image, and much higher in the other data sets. But the idea that this paper presents is contextual optimization, which let the model learn what it adds to before the class to the prompt, and then this idea increase the accuracy by a lot. It's up to more than 5% in Caltech dataset and more than like 30% in Flower and so on. The challenge in prompt engineering is like it requires expertise and it's extremely time consuming. So even as you can see in the before image, even just adding the word A before the class increases the accuracy by 4% from the original. So choosing the right prompt that make a very huge difference. And also we need a lot of time for word tuning. So in this paper, the proposed approach aims for auto-tuning prompt engineering and demonstrate its effectiveness in handling different image recognition tasks. And this method is called context optimization, or COOP for short. COOP models a prompt context word with learnable vectors, which could be initialized with a random value or pre-trained word embedding. And in this paper, they have two implementation. The first one is unified context, which shares the same context with all classes. And then the second one is class specific context, which learns specific sets of the context token for each classes. And you will talk more about those later. And also to demonstrate the effectiveness of COOP over other methods, they benchmarked it on 11 data sets, and the result shows that COOP is effectively turns pre-trained vision models into data-efficient visual learners, requiring a few as one or two shots to beat handcrafted prompts with decent margin. So yeah, the handcrafted prompts are as you can see in this image, the first three is handcrafted. They put the prompt, except the class, they put the rest of the words by themselves, and then the COOP trains to learn those words by itself. Okay, so a little bit about related works. In the vision language model, like the recent development in vision language models, particularly CLIP and Align, and they are like driven by advance of text representation, learning with transformers, and large mini-batch contrastive representation learning, and also web scale training datasets. Like CLIP benefits from 400 million created image text pair, while Align exploits 1.8 billion noisy image text pairs. And also prompt learning in NLP also is developing, and that the basic is to induce pre-trained language models to generate answers given close-on style prompts, which can benefit a number of downstream tasks such as sentiment analysis. So this close style prompt is very similar to COOP, which there is several places which you should put like the right word to make most sense. And also recently, Jiang et al. Proposed to generate candidate prompts through text mining and paraphrasing and identifying the optimal ones that gives the highest training accuracy. And also Shin et al. Introduced a gradient-based approach which searches for token with the largest gradient changes in the labeled likelihood. So these works are very related to the COOP. Also, yeah, methodologies. They use the CLIP, pre-trained vision language models, and also the CLIP can be used for several downstream tasks, including image classification, object detection, and semantic segmentation. And the CLIP leverages from joint representation of the visual and textual information, and it surpassed the state-of-the-art models. And CLIP consists of the two encoders. The one is image encoder, aims to map high dimension image into low dimensional embedding space. The architecture of the image encoder can take the form of CNN or visual transformers. And then the second encoder is a text encoder built on the top of transformers and aim to generate text representation from NLP, natural language, given a sequence of the words, also known as tokens. And the CLIP converts those into lower byte pairing encoding, which is essential, which is like the numerical ID, unique numerical ID to each token. Also, CLIP is trained to align the two embedding space learned for image and text respectively. So yeah, the idea of the training in CLIP is that it maximizes cosine similarity between the matched pairs, the text and the image features, and also minimize the cosine similarity for all other unmatched pairs. Here is the overview of the CLIP architecture. So they have contrastive pre-training, and then they use zero-shot prediction to do the detection or segmentation or any other task. Okay, so yeah, the zero-shot transfer refers to the ability of pre-trained vision language models to generalize to new categories without additional training data. So yeah, this can be achieved using textual prompts to guide the model towards the desired output. And a CLIP in a way is also zero shot, and it pre-trained to predict whether the image matches the textual description. So yeah, there's a little bit more about the concepts of the CLIP, and there is like image features as F, and then also there is VI, the set of the weight vector generated by text encoder, and then the clip predicts and the prediction probability is computed as this. And here is cosine, refers to the cosine similarity between generated text tokens and the image feature. Yeah. Also, COOPs and the context optimization avoids manual prompt tuning by modeling context words in the continuous vectors that are end-to-end learned from data, while the pre-trained parameters are frozen. And also, yeah, the idea behind this is to minimize the classification loss. Also, yeah, the COOP had two methodology. The first one is unified context. In this method, the token shares the same context with all classes. So like this V1, V2, VM are shared across all classes. And yeah, and then yeah, this VI gives to the text encoder GI. And then the forwarding the prompt T to the text encoder, we can obtain the classification weight vector representing a visual concept. The prediction probability is computed very similar to CLIP here. Also, as you can see in the above the token T, the class is placed at the end of the token. And then we can also put the class in between, which increases the flexibility for learning. And in this case, the prompt can be cut short right after the class or a little bit after the class, and can add some extra words to make it more, can add a little bit more cells for supplementary descriptions. Yeah, and the other one is class-specific context. In this case, the model is forced to learn different token for each classes. So as you can see, like V1, V2, V3 is not similar to V1, V2, V3 if like it's different classes. Here IJ define the classes. And this approach is useful for some like fine-grained classification tasks. Yeah, so they test their results on 11 benchmarks, as you can see here. And they used 1, 2, 4, 8, and 16 shot learning for shots for training respectively, and deploying model in full test sets. So handcrafted prompts for these data sets are written in the right side. Okay, yeah. So the training details for COOP, the COOP has 4 versions: positioning the class token at the end and the middle, unified context versus class-specific context. And yeah, for ResNet 55 is used as an image encoder backbone, unless it's specified otherwise. And also they used visual transformers. And all models are built on the top of CLIP open source code. And then COOP's context vectors are randomly initialized by drawing from zero mean Gaussian distribution with standard deviation equal to 0.02. And the baseline methods are 2 for a COOP. The first one is a zero shoot clip, which is based on handcrafted prompts, as we saw in this image in the right side. Yeah, and then they use like for generic objects and the scenes, they use like a photo of a class. And then for fine-grained categories, a task relevant context is added, like the type of the pet or the type of the food. And when it comes to specialized tasks such as recognition texture, the prompt is customized as the class comes first and then the texture comes after that. And the second one is the linear probe model. And the recent study on the few short learning uh, shows that the training a linear classifier on the top of high quality pre-trained models features can easily achieve performance that is on the bar with the state of the art few short learning methods, which are often much more sophisticated. So yeah, this linear probe was introduced by the paper, which says that it can achieve better results. Yeah. So here's the result of the COOP with us in some data sets, and then the average over all 11 data sets. So first we look at the comparison with handcrafted prompts. And here the default model is clip plus cop. And then this M indicates the so the M indicates the context length, and the end mid indicates if the class is at the end or in the middle of the token. Yeah, from this average performance, we can see that clip plus COOP is much better than the linear probe or a linear probe or zero shot clip, and given more data, it can achieve much higher result. And this one is the result of the COOP over the state-of-the-art models on the following data sets. As you can see, the COOP achieves much like over 45% accuracy in the Euroset data set, and much higher accuracy in all other data set except this Oxford Pets and Food 101. Also, here is the result of the COOP, clip plus COOP in these two data sets. And as we can see, it lost the momentum in the performance improvement, even with more shots are used. And the authors assume that this is because of the overfitting, and they recommend that like using higher regularization, like increasing the weight decay, can improve the results. But despite this, as we can see in the average, the COOP, clip and COOP has the overall result is strong enough to serve evidence that the COOP's is capability of learning task relevant prompts are data efficient in a data efficient manner. So yeah. So here's another evaluation study on context length and vision backbones. Some suggest that having shorter context can benefit domain generalization due to the less overfitting. But as we can see from the result, that the longer the context, the better the results. And also, when we put the class in the middle of the context, we achieve a little bit higher accuracy for with 8 number of contexts. And then the overall, the putting the class at the end gives a higher accuracy when we have like 16 number of context words. Also, as you can see here, the clip plus COOP outperformed the zero shot clips with all kind of backbones. And obviously, the more advanced the backbone, the higher the accuracy. As we can see here, Vision transformers achieve the highest result. And also, there has been some comparison between prompt engineering and prompt assembling, and also the COOP method. And as we can see, the kube outperformed the both prompt engineering and assembling with all kind of backbones. And the last slide is about the random versus manual initialization, and we don't we don't see that much difference as long as we have some like good manual initializations. But the authors usually recommend random initializations, which works better nearly in all cases. And then in the right, the table 5 summarize the kube method with other fine-tuning methods on ImageNet. And as we can see, the kube has much higher accuracy and higher difference with zero-shot models. Yeah, this is all. Thank you for listening.